Okay, so we've been talking about functions, and we still have plenty to say about functions. So here's the main idea for today, is that we have combinations of functions. So we could say, suppose that we're given functions f with domain d sub f and g with domain d sub g. So there's nothing like technical about that. I just I wanted both of their names to be of the domain to be d, but the one corresponding to f, it has a subscript f, so it belongs with that one, and subscript g, so it belongs with that one. Then we can combine them in the following kind of way. So we can make a new function in the following kind of way. So for addition. Now this is just like if we were given two numbers, say 3 and 5, we can make a new number by adding them together. 3 plus 5 is 8, a new number. All right. So what I'm saying is that given two functions, we can combine them to make a new function, and we could do it like this. So now, for a mental model of functions, again, sort of think of them like machines where you give them inputs. So like here's the f machine. You give it an input x, and then out comes what we're going to call f of x. And the g machine is similar. You give it an input x, and then out comes the output that we're going to call g of x. All right. Well, here's a way to make to take these sort of two machines, these two little machines, and combine them into a bigger machine. We can say, all right, suppose that we say, all right, we'll take this, take a copy of the f there, and take a copy of the g there. And we'll put it all inside of like one big box. So it's like all inside of this one big box here. And we'll say that we give an input to the box like this. So an input goes like that. And then inside of the box there's like a little splitter, like a cable splitter, and it splits it like this, so that f gets an x and g gets an x, so that here we have an f of x and a g of x, and then now these are going to combine back together, and the way that we're going to combine them is with an add. And so what we observe come out is this, f of x plus g of x. So we sort of, run f. Oops. Every once in a while, my how do I get out of there? Is it this one? Yeah. we run the f machine and it makes f of x. We run the g machine, it makes g of x, and then we combine those two results together to get f of x plus g of x. Okay, so the name of this function is f plus g. That's its name. All right. So what we're saying is that the function f plus g works like this. F plus g evaluated at x is f evaluated at x plus g evaluated at x. All right. Not very complicated in the end, sort of summarizing it like that. But the question that a question I want to consider is what is going to be the domain? Of f plus g. So, you know, if this is the f plus g machine, so if that's it, so that's how it works, that's what it does. But, and, you know, if you take the cover off, you know, and look inside, you know, like looking inside of your TV or whatever, you know, unscrew it and look inside and say, oh, look, that's how it works. Well, in order to do f, that means that the input has to be in df, in f's domain. You have to be able to do this part. And to do this part, the input has to be in dg. So in order to be able to do the whole thing, that means that the input has to work for that part and for that part, which means it has to be in df and also in dg. So what is the, you know, we've got a name for that, the set of all things that are in this set and also in that set. The intersection. So the domain has to be the intersection, df intersect dg. So an example would be something like this. Something like if we say that f of x is x squared on 3 to 42, and g of x is 10 minus x on negative 20 to 19. So if we have those two functions, meaning that here's a function defined by that expression, and that's its domain. Here's another function defined by that expression, and that's its domain. So now, understand that, you know, I could say, you know, what's f evaluated at 5? And then the answer would be, well, take 5 and square it. That'd be 25. And then what's f evaluated at 10? Well, take 10 and square it. That'd be 100. But if I ask what's f evaluated at 2, then what are you supposed to say? That it's not defined. It's not defined because that's the domain. So the only inputs that are allowed are 3 to 42, including 3 but not 42. Now I'm not saying that you know, we've suddenly forgot how to square 2. I'm not saying that. I'm just saying that this function f, its domain is said to be 3 to 42. It would be just like, in principle, over there in that vending machine, there could be M&Ms. That's a totally reasonable thing for a vending machine, but it may not be the case that there are M&Ms in there. Okay? Fine. So the domain, the expression, for f plus g would be f plus g evaluated at x would just be, you just add those two expressions together. That'd be x squared and then plus 10 minus x. So that's its expression. But then the domain, so you know, we could think about it for a second. So is it possible to evaluate g at 2? Is 2 part of G's domain? It is, right? So we could plug 2 into G, but we can't plug 2 into F because it's not part of F's domain. So 2 is not part of the domain of F plus G. Similarly, for F, we could plug in 30 because 30 is in there. But for G, we can't plug in 30 because 30 is not in there. So the set of all things that are in both would be the intersection of those two. So 3 to 42 intersect negative 19 to 20. And, you know, we've done this before lots of times, so we can do it real quick. So we'll plot those 2 intervals there. So open at negative 19, and then closed at 3, and then open at 20, and then open at 42, so the shaded is sort of saying the part where F is defined up here, and then this is saying the part where G is defined. And you can see the part where they're both defined is where they're both shaded. So over here like at negative 25, neither one of them is defined. And then we start moving to the right. Okay, right there, G's defined, but F isn't. So we need to go a little bit further. Oh, right there, 3, they're both defined. So they're both defined starting at 3. And then they're both defined all the way up to 20. Oh, I made an error, didn't I? I was looking at y'all, and I kept getting, and I was getting the the face, and I was trying to figure out what it was. So these are backwards, right? This look at that. I did it everywhere. Is that what y'all were giving me the face about? Okay, good. I was worried it was something serious rather than something silly on my part. All right, so this should be negative. Oh, I did it there too. So here, here, like that. All right. So, you know, again, back here at negative 25, neither one of them is defined. And then they both become defined at 3, and then they're both defined all the way up to 19. All right. Any question about this one? So, you know, what we're saying is that the sum function, its expression is given by that, and its domain is that. Now, we're not saying that concerning that expression, x squared plus 10 minus x, that you know, if we were to just find this out in the wild, say, you know, we're just walking in the woods and then we found that, that doesn't mean that these are the only numbers you'd ever be allowed to plug in. No, what we're saying is that if you have a function f with that domain and g with that domain, then the sum function is will have that domain. Okay. Well, continuing that page. We can do subtraction, which is just you know, f subtract g. So f subtract g evaluate at x is exactly what you think. It's f evaluated at x subtract g evaluate at x, and its domain is going to again be the intersection for the same reasons. So, you know, we've got subtraction. It works exactly like you think. We have multiplication. So that's f multiply G, and that is a solid dot. And just like that, I've always written solid dots for multiply. And if you don't, if you think it's weird that I'm saying that, then don't worry about that. It'll become clear why I'm saying that's a solid dot in just a moment. So f multiply g evaluate at x is just f evaluate at x multiply g evaluate at x. And its domain is the intersection for the same reasons as before. And we also have this division. So f divide g, which is also written very commonly like this. So f divide g evaluate at x is f evaluate at x divided by g evaluate at x. And its domain is almost the same. So they both have to be defined. But so that means, in order to even evaluate this, that means that you have to be able to evaluate f, and you also have to be able to evaluate g. But in addition to that, because g is in the denominator, what else do we need? G has to be non-zero. So it's even more restrictive, so intersect g of x not zero. All right. Fine. So we can do all those things. These are things we can do with functions, and we can do all those things with numbers. We can add, subtract, multiply, and divide numbers. We can add, subtract, multiply, and divide functions. And all of these things, add, subtract, multiply, and divide, their diagram looks like this diamond where, it's like this, where you split and then recombine with add or subtract or multiply or divide. They all have this sort of diamond shape. But the new one, the one that we really want, the reason why functions are sort of center stage in math is this new one that we mentioned last on Friday, composition. So now what it is that for all of the ones that we've just said, we made this diamond shape where we said, well, we're going to do f by itself and g by itself, and then combine them later with arithmetic. But rather than that, what we're going to do is we're going to use the output of one function as the input to the other function. All right. So it is denoted like this, so f and then an open circle and a g. So you need to be careful when you're drawing stuff, and that's why I said this is a solid dot. So this is an open circle, and this is just another bit of punctuation, like the division symbol is a bit of punctuation. So f composed with g. So in this case, it looks like this: f composed with g evaluate at x is defined as f of g of x, like so. And the diagram is notably different, because the way it works now is that, notice that we take the input and we give it to g first. So it looks like this. So x to g, like that. And then g makes its output g of x, and we're going to use that as the input to the f function. And then now it's going to make f of g of x, like so. And so you can imagine putting this in one big enclosure, building a big box around it. So we've got some big machine, and the name of this big machine is f composed with g. All right. So you can sort of imagine like covering this up and saying, well, x goes in, and that's what comes out. And just like we alluded to last time, The reason why this is going to be an important point of view is because it's like an assembly line. You're saying, well, first you do this. Oh, I keep mashing that button. Well, now I think I turned it off. Oh. Okay. Sorry. I don't know what it's doing now. All right. You can do it, machine. All right, so now we're back in business. Okay, fine. So now here's a page of facts that you already know. So we're going to do a whole page of stuff that you already know, and the reason is that I want you to be able to look at this stuff that you already know, and then we're going to start talking about stuff that's new. But I want you to be able to relate it back to this stuff that you already know. All right. In fact, this is stuff that we did very near the beginning of the semester. So concerning addition. Is the additive identity is 0. The reason why is that x plus 0 is x for all x. So that means that adding 0 is the same as doing nothing. So 0 is neutral with respect to add. All right. Similarly, the numbers x and y are called additive inverses. When? So let's. Can you remember what the rule is? So it is that when you add them, you should get something. What should you get?
0.
You should get 0. And the reason why we're interested in 0 is because 0 is the additive identity. So to way overstress the pronunciation of this idea, it's saying that two numbers are called additive inverses when you add them, and the result is the additive identity. Okay? One 1.3. The formula for additive inverse is negation. Meaning that given any number, the way to find its additive inverse is to negate. The additive inverse of 8 is -8. And the additive inverse of -4 is -4. And of course, normally you call -4 just 4. Now, the reason why those things are true, for example, in the case of 8, the additive inverse of 8 is -8 because when you add 8 and -8, what do you get? 0, which is the additive identity. All right? And then 1.4, all x have an additive inverse. All right? So all of them have one. For example, what's the additive inverse of 9? -9. What's the additive inverse of 0?
-0.
-0, which is the same as 0. So 0 is its own additive inverse because 0 plus 0 is 0, which is the additive identity. All right. Then, with multiplication. 2.1. The multiplicative identity is what? Is 1. The reason is because x multiply 1 is x for all x. That means that 1 is the element which is neutral with respect to multiply. Or, if you like, multiplying by 1 is the same as doing nothing. Just like adding 0 is the same as doing nothing. All right. 2.2. X and y are called multiplicative inverses when what? So by analogy to this. Yeah, when you multiply them and you get 1. The multiplicative identity. And again, to really overstress the emphasis of what's being said here, two numbers are called multiplicative inverses when you multiply them and the result is the multiplicative identity. Just like two numbers are said to be additive inverses when you add them and the result is the additive identity. Now that seems, I can totally appreciate that that sounds a little bit overbearing, but we're about to start doing something new, and it's my hope that that stress, that overstress, will be your guide when we're doing the new thing. So 2.3 here, the formula for a multiplicative inverse is, well, for add it's negation, and for multiply it's reciprocal. So, for example, what is the multiplicative inverse of 2/3? 3/2. Because when you multiply 2/3 and 3/2, the result is 1. Similarly, the multiplicative inverse of -4 is 1 over -4. Because when you multiply -4 and 1 over -4, the result is 1. All right. And the question now is which numbers have a multiplicative inverse? Well, they all have an additive inverse. Which ones have a multiplicative inverse? Everything except 0. All right. So now, when we're talking about add, these 4 things. When we're talking about multiply, these 4 things. They're analogous. 1.1, 2.1, 1.2, 2.2, 1.3, 2.3, 1.4, 2.4. So they're analogous. These are all things that we already knew. But now, instead of talking about add and multiply, we're going to talk about this new thing. We're going to talk about composition. And we want these 4 things. For composition, we want to know what the identity is. We want to define what it means to be compositional inverse. We want to figure out a formula for computing a compositional inverse. And we want to know which functions do have compositional inverses. Because just like not all numbers have a multiplicative inverse, not all functions are going to have a compositional inverse. All right. So, for composition, the first thing we'll need is a composition identity. All right. So now, before you got to UTD, of course, you knew 0 and you knew 1, and you knew that adding 0 does nothing, and you knew multiplying by 1 does nothing. But you might not. So 1 and 0, 0 and 1 are quite important and well known. The composition identity is just as important, but it's less well known. It's not so likely that you've heard of it, but you'll need to know it from now on. The composition identity is the function whose name is ID, so ID, and it's given by ID of x is just x. All right. So you gotta pay close attention to the kind of thing that we're talking about. So when we're talking about the additive identity, that the kind of thing that has to be is a number, because we're adding numbers. And we're talking about the multiplicative identity, the kind of thing that has to be is a number, because we are multiplying numbers. But if we're talking about the compositional identity, the kind of thing is a function, because you compose functions. All right. So that's it. And then as a diagram, it sort of looks like this: ID of x. So x goes in, and then x comes out. So it's kind of like just a little strip of conveyor belt, really. It's sort of like x, and then just x, right? It doesn't do anything. If you imagine like an assembly line, with little stations and stuff on conveyor belts, that x just straight down the line. Nothing happens. All right. So to see why this is the identity function, well, when we were doing addition, when that's what we were doing, the reason why 0 is the additive identity is because x plus 0 is x. Okay, and when we were talking about multiply, also besides x plus 0 is x, it also works the other way around, obviously. And then when we were talking about multiply, x multiply 1 is x, and 1 multiply x is x. And now what we want to show is that the similar thing happens with composition. So let's consider f composed with ID. Let's consider, what is that? Well, f composed with ID, and if we evaluate it at x. Now, according to our definition of composition, so f composed with g evaluated at x looks like that. So in some sense, this right-hand side is how you can write it without the circle. So how do we write this without the circle? So it would be f of ID of x, right? Like that. But we have a formula for ID of x. What is ID of x? Just x. So that means that now we can say that this is f of x, like that. And so what it's saying is that well, if you do this, that's the same as doing that. So what that's saying is that f composed with ID is the same as just f. So composing with ID apparently doesn't change the result. But if you think of this in terms of assembly lines in machines, I claim that this is obvious, because in this order, it's saying that the input is x, and first it visits ID. Okay? So it would look like this. X visits ID first, and then out comes, well, for the identity function, if x goes in, what comes out? X. And then now that visits f. And then out comes f of x. So that is just like a piece of a long piece of conveyor belt. That's all that it is. So it looks like this: x, and then all the way over to the f machine, like that. So if we take the f machine and we take that that input conveyor belt and we stretch it longer or make it shorter, does that affect? That doesn't affect it. All right. Similarly, we need to do it in the other order. So ID evaluate at f. ID composed with f evaluate at x. So how do we write this without the circle? So it'd be similar to this one, but in the other order. Mm-hmm. ID of f of x, like that. And now, you know, how about this? Well, according to the definition of ID, whatever you give it as input, that's its output. So if you put a 5 in, a 5 comes out. If you put a 55 in, a 55 comes out. If you put a giraffe in, a giraffe comes out. Whatever is put in is what comes out. So whatever I'm putting in here, ID of whatever I'm covering up, that's what comes out. If it's an 8, an 8. Well, what are we putting in? An f of x. So what comes out? F of x. So what we're saying is that doing this is the same as doing that. So that's telling us that ID composed with f is just f. And again, from the point of view of assembly lines and machines and things like this, that's saying saying this. So if we first do f, and then we get that output f of x, and then we say, and now you're going to go visit the ID machine. Well, the input to the ID machine is f of x. What will be its output? F of x, of course, because that's how the ID machine works. But that's just like saying that, well, suppose that we take the f machine, like so, and then instead of it having like a normal amount of conveyor belt after it, what if we like really stretch it out, like make it that long? No, no difference. Curious. So, you know, adding 0 is the same as doing nothing. Multiplying by 1 is the same as doing nothing. And composing with the identity is the same as doing nothing. Now, we have to do it in both orders because these functions represent processes, and the order is going to make a difference. So an example would be something like a typical human example would be something like, well, if you want to have company over and you're going to prepare dinner, say, then, you know, making a big dinner almost always entails messing up the kitchen. That's part of it. So then, you know, to get things back to the way they were, that usually means that after you've entertained guests and they leave, then you've got to spend some more time cleaning up the kitchen. Cleaning up the kitchen is the inverse process of messing it up. And that's just sort of the way the world works. But here's a way that the world doesn't work. You can't say, well, I don't really feel like staying up late after my guests leave, so I'm going to go ahead and clean up the kitchen now before I make a mess. That way, it'll be clean when I'm finished. Doesn't work that way, right? You can't like you can't clean it up before. Okay, so that's why you have to, where functions are concerned, you have to consider the order. Now, we need a definition of what does it mean for two functions to be composition inverses. All right. So functions f and g are composition inverses when, so let's see if we can discover it. And this is by analogy to this now. So two numbers are called additive inverses when you add them and the result is the additive identity, and two numbers are said to be multiplicative inverses when you multiply them and the result is the multiplicative identity. So what is the condition to say when two functions are composition inverses? You have to compose them and get the composition identity. When f composed with g is ID, and both orders, g composed with f is ID. Two functions are composition inverses when you compose them and the result is the compositional identity in both orders. So now, that's a correct way to say it, but for some circumstances it's more convenient to write it like this. So f, oops. So f composed with g evaluate at x, that would be ID evaluate at x, like that. So and g composed with f evaluate at x is ID evaluate at x. But what is ID evaluate at x? Just x. So this would be f composed with g evaluate at x is x, and g composed with f evaluate at x is x. So this last, this first one is sort of like the definition. This is like you know, the mathematical definition. But for the purposes of doing exercises, usually this is the one that you need to know. That one right there. So an example of using it. So for example, we could say something like, well, show, no, not show, but rather determine, oops, if p of x equal to 3x squared plus 5 and q of x equal to x minus 5 divided by 3 square root of all of that are composition inverses. So determine if they are. All right. So this is just like at the beginning of the semester when I gave you a question like, you know, determine if 3 and 5 are additive inverses, and then what you needed to do was add them and say, well, I got 8, and that's not 0, so they're not additive inverses. So determine if they're composition inverses. So what you must do is compose them and check and see if you get the compositional identity. All right. So P composed with Q evaluate at X. Well, writing this without the circle, that's P of Q of X, like that. And then now we can start plugging in the various parts. So, you know, I'll cover up the Q for a moment and just say, well, that's what P does. It takes its argument, squares it, multiplies by 3, and adds 5. So then I'll write it like this. So 3, and then Q of x, square that, add 5. And now I'll replace Q with what it does. So Q does that. So 3 multiplied by square root x minus 5 divided by 3 square add 5, like that. Okay, so now what we want to do is that if they really are inverses, if they are, then this should simplify all the way down to what? To x, right? If they are inverses. Okay. So does any cancellation happen? Yeah, you can see that the square root and the square, they'll cancel. All right. So that would be 3 multiplied by x minus 5 over 3, and then add 5. Now will anything cancel? The 3's will cancel, right? This multiply by 3 and divide by 3, those cancel. And so then we have x minus 5 and then add 5. Now the 5's cancel. All right. So we get x. So notice what's being said. We're saying, okay, take that x, take the input x, and what I want you to do is subtract 5, divide by 3, compute square root. And after you've done that, square it, multiply by 3, and add 5. And that's altogether a complicated way to say, take that x and do nothing. Just hand it right back to me, please. This is sort of a very loud way to do nothing with the x. So does this mean that they're compositional inverses? Not yet. Not yet. It's just like cleaning up the kitchen and making a mess are inverses of each other, but only in one order. So we only know that they're inverses in this order, but we need to check the other order. So Q composed with P evaluate at x is Q of P of x. Are we running out of time? I hear packing. Oh no, we still have plenty of time. So this will be square root. Seeing what Q does, Q takes its argument and then does argument, subtract 5 all over 3. So then P of x, subtract 5, divide by 3, like that. So that's what Q does. And then I can replace P with what it does. So P does this, 3 x squared, add 5, subtract 5, divide by 3. And then if they really are inverses, then we would expect to be able to simplify this all the way down to x. All right. So then if we drop those parentheses, the 5's would cancel. So that we have 3 x squared over 3, like that, inside of the square root. And then the 3's cancel, so that we have the square root of x squared. And so what's the square root of x squared?
X.
It's not x. It's the absolute value of x. Huh. So did it simplify down to x? It didn't. It's not x. So now what we're saying is take the x, square it, multiply by 3, add 5. And after you've done that, subtract 5, divide all that by 3, and compute square root. So that's, in some sense, a very loud way to say, take that x and compute the absolute value of x. So, are these compositional inverses? They're not. And In some sense, you could say they almost were. They almost were. So now, you know, there'll be you know, this is an example of why you have to check both orders, because it's totally possible for them to be inverses in this order but not in that order. And then to confirm that they really are compositional inverses, you have to show one and also the other. All right. Any question about this this idea? All right. So then, just as for the matter of foreshadowing, what are we going to do next time? So, you know, the formula for additive inverse is negate. So if I give you a 7, the additive inverse is -7. And the formula for multiplicative inverse is reciprocal. So the multiplicative inverse of pi is 1 over pi. What we want to be able to do next time is a formula for composition inverse. If I give you a function, how do you compute its composition inverse? All right. So I hope you'll have a wonderful Monday.